Hi, welcome to mock graph number 2. We will start with question 1. Draw the structure of molecules whose UPAC names are provided below, or name the molecules according to UPAC, whose skeletal structures are provided below. If necessary, indicate the stereochemistry as cis trans, EZ, and or RS. Okay, we start with the molecule number A. Okay, first we have to identify the main group. The main group is the alcohol. Okay, and the main chain will be the 5-member ring. That means this has to be a cyclopentanol, isn't it? But we also have a double bond here that is in position. Remember, if the alcohol is the main group, we will have one here, two here, here. In position 2, we have a double bond. That means that it's not cyclopentan, it has to be cyclopent 2 enol. Okay? And now once we have the main group and the main chain, what we have to do is to check the substituents that has the molecule. Okay, we have in 4 position, we have a methyl and a bromo. That means that will be 4 bromo, 4 methyl, cyclopent 2 enol. Okay? Now we go for the stereochemical information. If we have cis trans, this clearly the OH is going down and the bromine is going down. That means that will be cis. Cis for bromo, for methyl, cyclopentanol, cyclopent 2 enol. And if we want to know if it's R on S, we can do very easily. In this stereocenter, in the first stereocenter, this is 1, 2, 3. That means this R, but has to be S, is 1S. Here is 1, 2, 3. And again, it's S, but has to be R. 1S, 4R, cis for bromo, for methyl, cyclopent 2 enol. Okay? Good, then next one, we have to draw a structure of 4Z, 5-isopropyl, 3-methyl, oct, 4-enoic acid. Okay? First of all, is octenoic acid, means 8. Acid means carboxylic acid. Oct means that it's 8 carbons, the main chain, and that we have a double bond in the position 4. That means I wrote a 8. 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, and then here I put the carboxylic acid. In position 4, 1, 2, 3, 4, I put a double bond. Okay, and then I will put the substituents. In position 3, 1, 2, 3, I have a methyl. In position 5, 3, 4, 5, I have an isopropyl. Okay, and now I have to check if my compound that I draw is Z, or I have to change the double bond. Okay, clearly here the big group of this carbon will be this group, and here the big group will be this group. That means that is Z. That means that is correct. Okay. C, draw the structure of para-iodo-toluene. Okay, para-iodo-toluene, Remember that toluene is this with a methyl, a benzene with a methyl, and then para means 1,4. That means that we have the substituent here. Next one, name the following molecule. This is an ether. I recommend you that when you have an ether, divide the ether into two substituents and name one substituent, finish it with "il", name the other substituent, finish it with "il", and then put ether at the end. That means if we follow this, this will be benzyl isopropyl ether. Okay? Next one, we have a ketone. The first thing that we need to do is to draw or to find the main chain. The main chain will be this. Okay, and now what the problem that we have is starting from the side that we have. The ketone is always in position 4. That means that we cannot choose any side to start. We go for the next rule, and the next rule is that we will start for the side that has the major number of substitutions with the lower number. That means the substitution has the lower number. If I start from here, I have 2, 3, 5. If I start from here, I guess I have 3, 5, 6. Obviously, it's better this. That means that I will start from this position. That means this is 1, 2, 3, 4, 5, 6, 7. Ept, ta, non because it's a ketone. And now I number the position of the ketone, that is 1, 2, 3, 4. 4 heptanon, and then I put the substituent, will be 2, 3 dimethyl, 5 ethyl. If I put it in order, alphabetical order, remember, will be 5 ethyl, 2, 3 dimethyl, 4 heptanon. Okay? Remember that ethyl is E, that means that it's before the not M. Remember that when I say D, T, etc., this prefix doesn't count in order to make the alphabetical order. Okay? Well, F, draw the structure of 4-terbutyl cyclohexane carbaldehyde. Well, cyclohexane carbaldehyde is a ring of 6 with here an aldehyde. Okay, and then in 4 I have a terbutyl. Okay, and it has to be cramped. That means if I draw the aldehyde going up, the terbutyl has to go going down. Right? Next one, derive the structure of 2-butyl 4,5-dimethyl heptanoyl chloride. Okay, oil chloride means that it's an acid chloride. Heptan, that is 7 member rings. 1, 2, 3, 4, 5, 6, 7. Okay. I put here the acid chloride. And then I put the substituent, that is 4,5-dimethyl. 1, 2, 3, 4, 5. 5, 4, and then 2-butyl, that will be okay. Next molecule is this one. It says 1, 2, 3. This is an amide. That means I will cite this group and then I will cite the group attached to the nitrogen with N at front. That means this is 1, 2, 3, propanamide, and then I have to name this substituent that it will be N-methyl propanamide. Okay. Question 2 basically is write down the structure of the product of the following nucleophilic acyl substitution reactions. The pair of electrons of the oxygen attacks the acyl chloride, and remember the pair of electrons that are forming the oxygen carbon double bond is going to the oxygen to form this compound, and then the next step is, after the addition, tetrahedral intermediate, next step, formation of the double bond again, and departure of the leaving group, that is, in this case is the chloride, to generate this compound, okay, and then as usual I lost a proton because it's a charged compound to get the final ester. Okay, next one. Here basically what is happening is that the methoxide attacks the ketone. Again, in order to avoid to break the octet, the carbon double bond oxygen, the double bond is going to the oxygen, and what I generate is this intermediate okay, and then I protonate with the acid, the pair of electrons of the oxygen take the acid, and I will generate this hemiacetal. Okay. Okay. C. Provide the missing structures of a possible reactant for the given electrophilic aromatic substitution. Okay, remember that the electrophilic aromatic substitution, normally what we add is add alkyl chloride with aluminum trichloride, we form the carbocation, and this carbocation is reacting with the aromatic compound, with the benzene. Okay, that means if we break this, what we have is that we need to prepare this carbocation, that this is coming from the chloride, right? Next one, write down the structure of the expected major product for the following addition. Okay, remember when we add bromine to double bond, the first thing that we form is the bromonium ion. I will put it down, but you can put up, it's exactly the same. Okay, and then the bromine negative is attacking the bromonium ion, making the opening of the free member ring to generate the trans dibromide compound. Here you can see this will be the final compound. Okay, always we will get the trans product. Okay, E, write down the structure of the expected two products with the correct configuration for the following nucleophilic substitution. Okay, first of all, we need to decide which is the substitution that takes place. Basically, they say us that we get two different products, And importantly, this electrophile is a tertiary. That means that the only option that we have is to do SN1. That means if it's an SN1, the first thing is the leaving group is departing, and what we generate is this carbocation that is attacked by the alcohol. The pair of electrons of the oxygen will attack the carbocation by up and down. I mean, this is a planar molecule because remember that the carbocation has a hybridization sp2, and then the oxygen can attack from behind the slide or from in front of the slide, obtaining these two products. Okay. With the two different configurations. Okay. And in order to get the final compound, what we have is to remove one of the protons, and we will get these two compounds, that one is the enantiomer of the other. Okay, these will be the two compounds that we will get. Question 3. What is happening is that we have the addition of a hydrogen bromide to a double bond. The pair of electrons of the double bond will attack the proton, while in order to don't break the octet rule, the pair of electrons of the hydrogen bromine bond are going to the bromine. Okay, we generate this carbocation plus bromide. This is far away of our course. What will happen is that now the bromide will attack the carbocation in order to generate the final alkyl bromide. Okay. Next, what we have is that we have a peroxide, and what is happening is that we have a homolytic breaking of this bond. That means one electron is going to each oxygen, generating the d radical. Once we have the d radical, one of the radicals react with a hydrogen chloride, also again with a homolytic rupture of the bond, and what we generate is the chloride radical plus the alcohol. Here we have a similar reaction. Again, the double bond is reacting with the radical of the bromine, obtaining the most stable radical that will be always the most substituted radical. Okay. The important thing that you have to take care and to check is that all the arrows that I draw only is half arrow. Okay, like here, half arrow, not a full arrow. Okay, this is because I am moving radicals, not pairs of electrons. Okay, and finally, when I join this radical and the radical of the hydrogen, I got the final bromoalkyl compound. Next one. I have alcohol and I add hydrogen chloride. The pair of electrons of the alcohol are taking the proton, and the hydrogen chloride bond is going to the chloride in order to avoid to break the octet. Okay, what I am doing in this reaction, basically what I am doing is converting this hydroxyl that is a very bad leaving group in water that is very good. Next step, the water is departing, generating this carbocation, which reacts with the chloride to get the final compound. Here, the pair of electrons of the nitrogen attacks the carboxyl compound. Remember, this type of reaction is addition, tetrahedral intermediate, and elimination. That means that this pair of electrons that are forming the carbon double bond, oxygen, are going to the oxygen to generate this intermediate, and then after this tetrahedral intermediate, we regenerate the double bond carbon-oxygen, and the leaving group, that is the chloride, is departing, forming this compound. Number 4. Answer the following question. Decide with a brief reasoning which molecule, A or B, is expected to react faster in a SN2 reaction if you use the same solvent and nucleophile. Well, basically the two structures are the same, the only that is changing is the leaving group. Here we have a chloride, here we have an amine. Which is better leaving group? The chloride. We can justify for a lot of things. First of all, it's more electronegative. Second of thing, chloride than not amine, not nitrogen. Second, the overlapping between carbon and chloride will be worse than carbon and nitrogen because they are in different periods. That means the chloride is by far bigger than the carbon. Okay, B decides which molecule is expected to react faster in SN1. What we are doing in SN1? In SN1, we want to stabilize the carbocation. Okay, which carbocation will be more stabilized? Well, in A, first of all, this is secondary. Okay, after the leaving group, this is secondary. What more? Also, we can stabilize by resonance with this double bond. And moreover, the chloride is better leaving group than not OH. That means everything indicates that will work better A than not B. Okay, C. Decide with a brief reasoning which molecule, A or B, is expected to have a higher boiling point. Okay? We have van der Waals forces in here, dipolar forces, and hydrogen bonding. While here we only have van der Waals or dispersion forces and dipole forces. That means the hydrogen bonding will make that this compound will be higher boiling point and higher melting point. Okay? Okay, D, decide which, with a brief reasoning, which molecule, A or B, is expected to have a higher pKa. Well, this is an alcohol, A is an alcohol, and B is a carboxylic acid. Carboxylic acid will have a higher pKa because it's an acid. And we can justify because if we check its conjugate base, we can do a resonance form that makes the conjugate base more stable, for this reason more acidic. Okay, E, decide with a brief reasoning which molecule, A or B, is expected to be a better nucleophile. We can do a reasoning that this compound B is stabilized because we have this resonance form like the one that we did before. Okay, this is coming here, this is coming here. That means that this compound B will be more stable than A will be more reactive, but be better nucleophile. Okay, next question is about tell which of the following molecules are aromatic, antiaromatic, or non-aromatic. Okay, A will be non-aromatic. Why? Because these four carbons are sp3. Remember that for the Huckel rules are cyclic, planar, all atoms of the cycle sp2 and 4n plus 2 aromatic, 4n antiaromatic. That means this simply doesn't follow the rule of the all atoms of the cycle has to be sp2. That means that non-aromatic. Next one, B we have cyclic, planar, all atoms has sp2. We can hybridize this nitrogen as sp2 because we have a pair of electrons. Okay, and we can put this pair of electrons in the pz orbital. And then we have 2, 4, and these 2, 6 electrons, aromatic. And the last one is planar, yes. Is cyclic, yes. Is all the atoms are sp2, yes, because this is a carbocation, will be sp2 hybridized. How many electrons we have? 2, 4, this is 0 because it's a positive charge. That means 4 electrons, anti-aromatic. Okay? Okay, question 5. For a two-step chemical reaction given below, they say step 1 is endoorganic, step 2 is exergonic, and overall reaction is exergonic. Okay? The energy of transition state for step 1 is higher than the for step 2. Rate of the reaction depends only on the concentration of A and B. Okay? Well, sketch a free energy diagram. Well, the free energy diagram, we know that the overall reaction is exorganic. That means if we have the starting materials, that is A plus B, if it's exergenic, will be more unstable than not the final products of the overall reaction that will be E and F. Then what we know is that the first reaction is endoorganic. That means that the first reaction C plus D has to be with higher energy than not A plus B. If we did it well, then C plus D has to be higher energy than CF, as you can see, and the second will be exergenic. Then they said the first energy activation is higher than not the second. Well, that means the first energy activation, we wrote it here. This is energy activation 1 of the first reaction is higher than the second reaction. We only have to do this. And this is the energy activation of the second. This is the transition state 1. This is the transition state 2. Okay, remember the transition states are maximums of energy. Okay. Okay, write the rate equation for this reaction based on the rate determining step. They say that the only important is A plus B. That means that the rate will be equal to a K, a constant, by the concentration of A multiplied by the concentration of B. And then if the state K equilibrium value of the overall reaction is being lower than 1 or higher than 1, and give a brief reasoning. Okay, we know that the final products has less energy than not the starting materials, the overall reaction. Okay, that means if the overall reaction, the final product has less energy than the starting material, this will be more stable. Remember that the equilibrium constant is equal to the concentration of the final products, E plus F divided by the starting materials, A multiplied by B. If we do this, because E and F are more stable than not the starting materials, A and B, the reaction will have tendency to go to the product. That means this will be bigger than not this number. If this number is bigger, if the number of the E, the concentration of E multiplied by the concentration of S is bigger, means that the constant of equilibrium will be major than 1. Okay? Question 6. Draw the mechanism for the following reactions. Okay? First question, here is BD free. This is exactly the same that BH free, but using a deuterium that is an isotope of the hydrogen, with 2 neutrons, with 1 neutron and one proton. Okay? And the first step is we have here this compound, then the borate, the borane, okay, is making a bond with the double bond. Okay, remember always the boron is added to the less substituted position of the double bond, and that hydrogen, or deuterium in this case, will be added for the most substituted position. Moreover, the boron and the deuterium, or the hydrogen, will come from the same site. That means that we will have this compound and then we treat this with hydrogen peroxide. Remember that only is we substitute the boron for a OH and keeping the same configuration. That means that the final product will be a Kranz product. Okay? Next one is the same compound, but now we treat it with mercurium. Remember, the first step will be always the same. We are forming the free member ring with the mercurium. Okay? And then the solvent, in this case the methanol, will open the free member ring of the mercurium by the most substituted part, because it's the position that stabilizes better a positive charge. That means that what we will have is this. Remember, we have an inversion. And then with sodium borohydride, the only that we do is to substitute the mercury by a hydrogen, and what we will get is this compound. Okay? And that's all. Thank you very much for your attention, and see you in the next mock exam.